Now we'll return to the M16 rifle. A rifle is really a single-cylinder car that kind of doesn't really repeat the action. So we're looking at a one-cylinder engine, so a gun is surprisingly similar to a car. So if we look at the M16 rifle, using the standard NATO 5.56mm cartridge with 60 grains of gunpowder, it works out to roughly 4 grams of powder and 4 grams of bullet. Now, how much energy do we get out of the gunpowder? Well, the term gunpowder covers at least a dozen different chemical formulations. So in about a half an hour's worth of research, I found a range of about 4,000 to 11,000 joules per gram in the gunpowder. And this was done in a lab, and they experimented by actually breaking apart real M16 cartridges. So this would be practical. What kind of muzzle velocity would we get out of the gun? Well, let's see what we can calculate. We take Q equals mass times specific heat of combustion, and we now know we're going to get about 4,000 to 11,000 joules per gram. So if I put in the 4 grams of gunpowder and I use the minimum and maximum value here, I wind up with the range of 16,000 to 44,000 joules being provided to these bullets. Now, Newton's third law kicks in here. When the gunpowder goes off, switch it in your mind to a bullet in a gun to 2 bullets plugged into the opposite end of a short piece of metal pipe. When the gunpowder goes off, it's going to drive its force forward and backwards. So by Newton's third law, we can cut it down to about 8,000 to 22,000 joules. Just divided this by 2. When I take my kinetic energy formula and rearrange to solve for speed, I get a muzzle velocity somewhere between 2,000 and 2,300 meters per second. So this seems to be a simple way of calculating our muzzle velocity. Then I look up what it really is in life, and I get this value, 990 meters a second and an energy of 1,700 joules. That's a pretty significant error. That's like 50% there, and on this number, that's like 75% error. So what did we do wrong? Are we totally wrong? On the right track? This is what you have to ask yourself when you're solving for these. And as I click, there we go. Now, a quick little bit of research produced a chart remarkably similar to the one with the internal combustion engine. Only about 32% of the powder goes towards kinetic energy. Virtually none of it moves the vehicle forward or the bullet forward. So it's almost the exact same percentage as a car. So what we have to do is downgrade the energy. The energy of 8,000 to 22,000, if we take 30% of that, 3 times 8 is 24. This is the energy range we get, and that energy will go to kinetic. And this gives me new values of 774 to 1284. And that is smack in between. When I average these, I get an average of 1,029 compared to 990. So that puts me smack in the middle of that range, and it works out to an error of only 3.9%. So once we take into account the efficiency of the shell, it turns out basic high school calculation can generate an answer that is only 3.9% off the accepted laboratory value. That's pretty good. And if you want, read this section here on why you had to downgrade the energy prior to the calculation, not after. It's not that important to you, really, but you should learn it, but it's up to you. Next, we'll move to the machine gun.